Hello everyone and welcome back to the class. In today's class, first of all, we will discuss relation between electric field and potential. So let's see it everyone. We know one thing from the work power energy chapter. Change in potential energy can be written as minus F dot dr. Correct? This relation we know from the work power energy chapter, where F is what? It is the conservative force. Correct? F is what everyone? It is the conservative force. So if work is happening due to the conservative force, then potential energy of the system will decrease. Here we are talking about potential energy of the system, everyone. Correct? For example, like we have pen here, gravitational force is acting downward direction. If I will release this pen from the here, so what is happening? It is going down. So gravitational force is acting downward direction. It is moving in downward direction. So displacement is also happening in the direction of gravitational force. That's why work is positive here. Correct? So work is positive here, but what is happening with the potential energy? It is decreasing, correct? That's why we have negative sign here. So if work is happening due to the conservative force, then potential energy of system will decrease. All right, this thing we knows already from the work power energy chapter. So here everyone, we are talking about the electrostatic force. Electrostatic force is also conservative force, correct? So here work is happening due to the conservative force due to the electrostatic force. So then again potential energy will decrease. We know one more thing everyone, du can be written as q del v, correct? Q del v, and this Fc can be written as QE, because now we are talking about the electrostatic force. So electrostatic force can be written as QE, correct? So this thing we have. Now QQ will get cancelled out, so we have del V equal to minus, and QQ will get cancelled out, so we have minus E dot dr. This thing we are getting. Now see it everyone, here we have negative sign. What is the sense of this relation? What it is representing? The sense of this relation is, if we are moving in the direction of electric field, then potential will decrease everyone. If we are moving in the direction of electric field, then potential will decrease everyone. So this is the direction of electric field, and we are moving in the direction of electric field. So what will happen with the potential? Potential will decrease everyone. All right. So if we have electric field and we want to change in potential, then we will use this relation. So if E is given and we want change in potential, then use this relation. And if V is given and we want a E, then use this relation everyone. And from where we are getting this relation? From the work power energy chapter, we have one more relation everyone, F equal to minus del U by del X. Correct? So this relation we know from the work power energy chapter, F equal to minus del U by del X. So use this relation here everyone. And F can be written as what? It is QE. Del U can be written as what? It is Q del V. QQ will get cancelled out and you will get relation between electric field and the potential. So when V is given, we want electric field, then use this relation everyone. And when E is given and you want change in potential, then use this relation, correct? So keep this both relation in your mind everyone, note down and give me thumbs up. Let's see it one question everyone. On the basis of this concept, choose the correct options. So here we have this electric field everyone, you can see it in this picture. This is a direction of electric field. This blue arrow is representing direction of electric field, and electric field is constant here everyone, correct? So we want potential relation between A, B and C point. So between this 3 point we want relation between the potential. So what we need to do it here everyone, if we will move in the direction of electric field, then what will happen with the potential? Then potential will decrease. If we are moving in the direction of electric field, then potential will decrease everyone. We know one thing everyone, change in potential equal to del V equal to minus E dot dr. This thing we know, correct? So del V equal to what? It is minus E dot dr. Here E is constant, so put out the integration, and integration of dr is what? It is a d. and after removing the dot product we will get cos theta. So after simplification we are getting everyone del v equal to minus E d cos theta. Correct? Where theta is what? It is the angle between E and D is representing here displacement. So here theta is what? It is the angle between E and D, everyone. So when the theta is 90 degree, then change in potential is 0. Means if you will move from A to B and B to A, then what is happening? If you are moving from B to A, so this is the direction of displacement and this is the direction of electric field. So we can see it here. Angle between electric field and displacement is 90 degree. Same thing will happen when we will move from A to B also. Means A to B, if you are moving, or B to A we are moving, then potential is not changing. Means potential is same. So from here we are getting potential at A point and potential at B point is equal. What about the C point? We know this thing, everyone. When we are moving the direction of electric field, then potential will decrease. So the potential at the C point should be less as compared to A and B point. So what is the correct relation here? VA and VB is equal and it is greater than to VC. So this is the correct relation, everyone. Hence, correct answer is option 4. VA equal to VB and it is greater than to VC. Note down, everyone. Let's see next question, everyone. If the potential in a region is expressed as V equal to 10xy minus yz plus 2xz, what is the value of electric field at the point 0, 1, 0? So here electric field we want, everyone, and electric potential is given in this question. And we know the relation between electric potential and electric field, E equal to minus del V by del x I cap plus del V by del y j cap plus del V by del z k cap. Correct? So del V by del x I cap plus del V by del y j cap plus del V by del z k cap. Alright. Now what is the potential, everyone? So potential is 10xy minus yz plus 2xz. So here with differentiation, here we are doing partial differentiation, correct? So if we are doing partial differentiation with respect to x, then only x is variable, y and z we will consider constant, everyone. This thing we know. So we are doing with respect to x. So we have 10xy, x is variable, 10y is constant, and differentiation of x with respect to x is what is the 1. So what we will get? We are getting here 10y, and here we have minus yz, correct? We are doing with respect to x, so yz is constant, so it is 0. Then 2xz, we are doing with respect to x, so here we will get 2z. Alright, now do it with respect to y, everyone. So if we will do it with respect to y, then what we will get? Now we are doing with respect to y. So first we have 10xy, correct? So y is variable, 10x is constant, so here we will get 10x, everyone. Correct? 10x we will put outside, and differentiation of y with respect to y is 1. So 10x we are getting. Then we are doing minus yz, partial differentiation. Y is variable, z is constant, so here we are getting minus. Here we are getting minus z. The next is 2xz. Here x and z both are constant, everyone, so it is 0. Now do it with respect to z. So in the first term we have 10xy, means z is not present, so it is 0. Whole term is constant here. Then we have minus yz, so we will get minus y. Then we have 2xz, so here we are getting plus 2x. Correct? So we have now del v by del x, del v by del y, and we have del v by del z also. Put in this equation number 1, everyone. That's all things. So we are getting E equal to minus del v by del x is what? It is 10y plus 2z. Correct? We are looking at 0, 1, 0, everyone. At this point we are looking. Correct? So here this is what? This is the x, this is y, and this is z. So x and z value is 0, only y is 1 we have. So x and z is 0 and y is 1. So if you will put here x and z value, then what we are getting? If I am putting, then I am getting 10 only. Z is 0 everyone. So here I am getting 10, and here what we will get, here I am putting x equal to 0 and Z equal to, we are getting 0. So we are getting here 0. Here y equal to -1, x equal to 0. So here we are getting -1. Correct? So now next thing is what? Now we have del v by del x, del v by del y, and del v by del z. So put in the equation number 1. So what we are getting? Del v by del x we got it 10. So it is 10i. Del v by del y is 0. So 0 j cap. Then del v by del z we got it minus. So it is minus k cap. Correct? This thing we are getting. Now multiply minus sign inside the bracket. So finally we have minus 10i cap plus k cap. Minus 10i cap plus k cap. Hence correct answer is option B. Minus 10i cap plus k cap. Note down everyone. Let's see next question everyone. If the potential at the origin is 0 volt, what is the potential at 3, 0 based on the electric field variation below? Correct? So here we want potential at this point everyone, at 3, 0. At this point we want potential. And this is origin 0, 0. And V initial is how much everyone? What is the potential at the origin? It is 0 volt. Correct? And at this point we want, what is the V final? This thing we want. So let's see how we can do this question everyone. We know that change in potential can be written as what? It is minus E dot dx. This thing can be written as del V equal to minus E dx. Correct? Okay. So here the del V is what? It is the change in potential, means final minus initial. Correct everyone? Now put this negative sign here, then it is V initial minus V final equal to E dx. This thing we will get. Correct? Now the next thing is what everyone? V initial minus V final is equal to what? It is integration E dot dx. Correct? What is the V initial everyone? V initial is given, it is 0 volt. V final we are finding here. What about this integration E dx? What it is everyone? So this integration E dot dx is nothing but area under the curve. This is what everyone? It is the area under the curve. Correct? So this is what? This is the area under the curve, and here graph already we have. So area under this graph or this curve is equal to what? It is equal to integration E dot dx. So let's see how much area we have inside this triangle. Just use here triangle formula. 1 by 2 base into height. Base is 3 everyone. And what is the height of the triangle? It is 10. So what we are getting here? Minus Vf equal to minus 15 volt. Minus I am putting on this side, so I am getting Vf equal to what? Minus 15 volt. This is the final answer everyone. Correct? Minus 15 volt. So I hope this thing is clear everyone. Note down. Let's see next question everyone. Find the potential difference between R1 and R2 position. So here we want potential difference between this R1 and R2 everyone. Correct? So what we are doing, first of all I am writing electric field due to this wire at x distance. So electric field due to this wire at x distance can be written as what is 2k lambda by x. So you can see it here, electric field is the function of x. If x will vary, then electric field will change. Correct? So if we will go far away from this wire, then continuously electric field is changing everyone. So what I am doing here, I will take one small region between this 1 and 2 position. And this region I am taking at x distance. Correct? And for this small region, we are considering electric field is constant. And length of this region is dx everyone. If I will write change in potential for this small region, so this change in potential can be written as dV equal to minus Ex dot dx everyone. Here, if I will remove the dot product, then cos theta will come. Theta is the angle between electric field and dx. And theta is 0 here. That's why the next step we will get minus Ex dx only. Correct? Because here displacement is happening in the direction of electric field. That's why theta is 0 and cos 0 is 1. So for this small reason, change in potential can be written as minus Ex dx. But we want between 1 and 2, so we need to integrate. So we will integrate everyone on both sides. And put Ex value also, which is 2k lambda by x dx. Now put limit of integration everyone, r1 to r2. So dv is what it is, del v minus 2k lambda r1 to r2 1 by x dx. So integration of 1 by x is what it is, log x everyone. So log x and then put limit of integration. So here we will get del v equal to minus 2k lambda log r2 by r1. Correct, this thing we will get. Now what we can do it, put this negative sign here everyone and use log property. So finally we are getting del v is equal to 2k lambda log r1 by r2. Correct, log property already we know that. So this properties we are using here, then this is the final answer everyone. Alright, so if we will move from 1 to 2 position, so change in potential is 2k lambda log r1 by r2. Note down everyone. Let's see next topic everyone, electric potential due to a disk. So here we have one disk and due to this disk we want potential. So what we will do it here everyone, first of all we will assume one ring on this disk everyone. Correct? So this is ring and let's suppose this is the center of the ring and the radius of the ring is small r and the radius of the disk is capital R. Correct? So this is small r everyone and this is capital R and this is center. And thickness of the ring is what it is, dr. And charge density is sigma everyone. Correct? And at this P point we want electric potential. And the distance between the O point and the P is what it is, x everyone. So the distance is how much? It is the x. So what I will do it here everyone, first of all I will write potential due to this ring at this P point. Let's suppose charge present on this ring is dq and dq can be written as what? It is sigma, circumference of the ring is 2 pi r and the thickness is dr. So 2 pi r, dr is the area of the ring and if we will multiply with the surface charge density then we will get charge present on this ring everyone, dq. And due to this ring, if I will write potential at the P point, so it can be written as what? dVp or dV equal to k dq, correct, under root r square plus x square. This thing we will get. Correct? Due to the ring, potential at x distance we knows. Correct? This thing already we have done, so we knows everyone. Now the next thing is what here? Due to the ring we got it, but we want here due to the disk everyone. Alright, so we need to integrate here. So we will integrate on both sides. Put here dq value which is sigma 2 pi r dr. divided by under root r square plus x square. Correct? And limit of integration. So limit of integration should be what, everyone? It is 0 to r. Correct? This is the limit of integration. R is the radius of the disk. So here small r is varying, everyone, and we are doing integration with respect to r, with respect to small r. Now next thing is what? Put constant outside the integration. Integration of dv is what? It is the v, 0 to r, and put constant outside the integration. So k is constant, sigma 2 pi r. So all are constant, put outside, 0 to r dr divided by under root r square plus x square. Correct? Now it is looking very complex, everyone, if we will do it integration here. So what we will do it, we will take order here. Correct? We will assume r square plus x square equal to u. This thing we will substitute. So what I am doing here, r square plus x square, I am assuming it is equal to u. So r square plus x square equal to u, I am assuming. Now do differentiation of this equation with respect to r or with respect to u, also you can do it. So what we will get, I am doing with respect to r. With respect to r, we are doing differentiation. Correct? So differentiate with respect to r. So what we will get? 2r, x is constant, so it is 0. And differentiation of u with respect to r is du by dr. Correct? This thing we are getting. Now the next thing is what here? It is du equal to 2r dr. So du equal to what we are getting, everyone? 2r dr. Alright. So r dr value is what? It is a du by 2. So now r dr equal to what? It is du by 2, everyone. This thing we will get. Now the next thing is what? Now we will do it one more thing, everyone, because now we are replacing small r in the form of u. So limit also we have to change. Correct? According to u. So we need to change this limits also. So let's see how we can change these limits. We have this, everyone, and we are assuming r square plus x square equal to u. So lower limit of small r is what? It is a 0. So if I will put r equal to 0, then what is the u? U we will get x square. And what is the upper limit of r, everyone? It is the capital R. So if I will replace small r with the capital R, so the upper limit of u we will get r square plus x square. So this is the limits, everyone. Lower limit and upper limit. This limits we will use now. So now we will replace u r with the u, everyone. This thing we will do it. Let's see it. What we will get. So we have v equal to k sigma 2 pi. Limit, lower limit is what? It is x square, and the upper limit is r square plus x square. Correct? RDR value is what? This thing also we got it. RDR can be written du by 2. So it is du by 2, and r square plus x square is u, so it is root u. So now this thing have you. Correct? Now we have this thing. Now the next thing is what? Take 2 outside the integration because it is constant. So this and this will get cancelled out, everyone. Now in the next step, what we can do it here, k sigma pi x square r square plus x square we have. Correct? So root u can be written as what? If it will go in the numerator, root u can be written as u power 1 by 2. If it will go in the numerator, then it is u power minus 1 by 2. Correct? Now do it integration, everyone. So v equal to k sigma pi. Integration of u power minus 1 by 2 is what? It is u minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. So what we will get, everyone? U power 1 by 2. 1 by 2. And limit is x square plus r square plus x square. So after the integration, we will get this step, everyone. Now the next thing is what here? Put limits here, and 2 we will write here. So we have v equal to 2 k sigma pi, and u upper limit is r square plus x square. So it can be written as root r square plus x square. Correct? Now put lower limit. So we will put a negative sign, and lower limit is x square. So u power is 1 by 2. So it is root u. So it is x only, everyone, because we have root x square. So root and x square will get cancelled out. Then we have only x. So finally we have this thing, everyone, and put k value also. And what is the k value? It is 1 upon 4 pi epsilon naught. So we have now v equal to 2 k value is 1 upon 4 pi epsilon naught sigma pi r square plus x square minus x. Now pi will get cancelled out, and this is 2 and this is 4. So this is 2, everyone. So finally what we have here, v equal to sigma by 2 epsilon naught under root r square plus x square minus x, and this is the final result, everyone. So note down this result and keep this result in your mind, everyone. This is important. So electric potential due to the disk is what? It is v equal to sigma by 2 epsilon naught under root r square plus x square minus x, everyone. So this is the final answer. Note down. Let's see next topic, everyone. Equipotential surfaces. So what is the definition of equipotential surfaces? It is the locus of all the points having the same potential. So it is the locus of all the points having same potential. So if you will connect same potential point, then we are getting one locus, and this locus is what? It is a equipotential surface. So let's suppose I have one plus q charge and I want to draw equipotential surface for this point charge, everyone. Correct? So due to this plus q charge at r distance, potential is, let's suppose, v, everyone, and the potential formula is what? It is the kq by r. Correct? If I will go on this side also, correct, r distance from this plus q charge, then potential is again kq by r. So here is again v. Correct? This distance is r, everyone. So in every direction at r distance from this point charge, potential is same, everyone. Correct? So potential is same. Now what I need to do it here, I will connect this all the points. So I am getting here one sphere, everyone. So this sphere is what? It is the equipotential surface. So now I will draw here one sphere, everyone. And this sphere is representing equipotential surface. Correct? So let's suppose this is the r distance. So here the potential is what? It is kq by r, and here is also kq by r. So potential on this sphere is same, everyone. And here we are not getting only just single sphere. Here we are getting n number of concentric spheres, and this all the spheres has some potential. That's why this all spheres are equipotential surface for this plus q charge. So here we are getting n number of concentric spheres, everyone, and this all the concentric spheres are equipotential surface. All right. So I hope this thing is clear to everyone. Note down. So here we are getting a spherical equipotential surface for the point charge. Now if I will move A to B, then what will happen? Let's suppose A point and this is a B point. So I'm moving A to B point. Then how much work we need to do it? So let's suppose at A point plus Q charge is present and we want to move from A to B. So how much work we need to do it? So work done required to move from A to B is equal to Q del V. Correct? Potential at A point and potential at B point should be equal because this both are present on equipotential surface. That's why potential at A and B should be equal. Correct? So V equal to VB, everyone. So what is the del V? Del V is 0. So what is the work done to move from A to B? It is 0, everyone. So if we are moving, or if we are moving one charge from one point to another point on the equipotential surface, then always work we will get 0. But if we are moving from one equipotential surface to another equipotential surface, then we will not get it 0, everyone. Then it is not necessary. But if it is same equipotential surface and we are moving one point to another point on this same equipotential surface, then work we will get 0 always. Alright. Now let's see its second point, everyone. Here electric field is always perpendicular to the equipotential surfaces. So draw here electric field lines. So if we will draw the electric field lines, so this is field lines, everyone, correct? So if you will look here, electric field lines and equipotential surface intersecting at 90°. Here also something is happening. This is the electric field and this is the equipotential surface. So here angle between this equipotential surface and this electric field is 90°. And this thing happen always, everyone. It is not only for point charge. If suppose we have one wire also, and for this wire if I will draw the equipotential surface, then electric field lines and that equipotential surface both are perpendicular, correct? So always it will happen. It is not only for the point charge. So you can see it here, electric field and equipotential surface both are perpendicular, correct? So note down this all things, everyone. Then we will move for the next slide. Let's see next, everyone, equipotential surface for electric dipole. So let's see it, what type of equipotential surface we will get for the electric dipole. So here we have positive charge and here we have negative charge. So this is the electric dipole, everyone. And now draw electric field lines. This is electric field lines, everyone. Correct? Now we want equipotential surface for this electric dipole, and we know that one thing, electric field and equipotential surface both are perpendicular. So electric field is always perpendicular to equipotential surface. So this thing we know is correct. So if you want here equipotential surface, so draw here one plane, everyone, and we can see it here. This plane is intersecting this electric field line at 90°. So angle between the field and this plane is how much? It is the 90°. So this is what? This is equipotential surface for electric dipole, everyone. And this is plane, correct? Because if it is positive charge and this is negative charge, so electric field lines we have in all directions. And if you will draw one perpendicular, so here we are getting one plane, not a line. correct? So this is a plan, everyone. Now let's see it. If we have positive charge, then what type of equipotential surface we will get? So now we have positive charge. So first of all, what we will do it here, we will draw here electric field lines. So let's see what type of field lines we will get. So this is field diagram, everyone, and we want equipotential surface. So we know one thing, equipotential surface and field lines always perpendicular, correct? So let's see what type of equipotential surface we will get for this. This is not an exact diagram, but approximately we will get like this, everyone. The rough diagram. So here we will get dumbbell shape, everyone, correct? So if we will draw the equipotential surface for this two isolated positive charge, so we are getting here dumbbell shape, everyone, correct? Note down. Now we want equipotential surface for the line charge. So let's see what type of equipotential surface we will get for the line charge, everyone. So let's suppose this is the line charge, and positive charge is present on this line or on this wire. We want here equipotential surface, correct? We knows one thing, everyone, electric field and equipotential surface always intersecting at 90 degree, correct? Both are perpendicular. So if I will draw here concentric cylinders or cylinder, so let's see what is the angle between the cylinder surface and the electric field. So now set electric field, everyone. So this is electric field lines. Okay, see it. So this is electric field lines, everyone, correct? So this is the direction of electric field and this is equipotential surface. So we can see it here. Both are intersecting at 90 degree. So for the line charges, we will get cylindrical equipotential surface. So this is our equipotential surface, everyone. So I hope this thing is clear. Note down. Let's see it next, everyone. Equipotential surface of a thin plane sheet with a uniform charge distribution. So now we want equipotential surface for thin plane sheet. So first of all, distribute charge uniformly on this thin plane sheet. Now draw electric field lines due to this sheet. So this is electric field lines, everyone. Correct? So this is the direction of electric field. And this is equipotential surface. Correct? So we can see it here. Here, angle between equipotential surface and field line is what? It is 90 degree. So this is the equipotential surface number 1. So n number of equipotential surface we will get due to this thin sheet. The second, everyone. So for the thin plane sheet, we will get thin plane sheet equipotential surfaces. Correct? So note down. Let's see one question, everyone, on the basis of this concept. The diagram shown below shows the region of equipotential surfaces. Consider the work done by the electric force in moving a unit positive charge from A to B in the following cases. So here we want work done by electric force and moving a unit positive charge from A to B in following cases. So here we have 4 cases, everyone. In the case 1, what is happening here? This is the A point, correct? And the potential of this A point is what? It is a 10 volt because it is present on the surface. And the potential of the B is what? It is a 40 volt, everyone. Correct? So if you want work done in the first case, so what we will write here? We know that work done by the conservative force is equal to what? Q, V initial minus V final. So this is initial, everyone, and this is final position. We are moving from A to B. That's why V potential at A point is what? It is VI. Correct? And VI and VF, both things we know. So in the case 1, if I will find work done, so it is Q value is what, everyone? Q is 1. What is VI? It is 10. What is VF? It is 40. So how much we are getting? W1 is equal to a minus 30 joule. This is the work done in the first case. Now let's see it. Second case, everyone. Case number 2. In the second case, if we want work, so in the second case, again, we have unit positive charge. And we are moving this unit positive charge from A to B. Potential at A point is what? It is 10 volt. And potential at B point is what? It is 40 volt. So again, we are getting same result. Minus 30 joule. Correct? Now let's see case number 3, everyone. If you look at the case 3, in the case 3, potential at the A point is again 10 volt and the B is what? 40 volt. Here, if you will look at the A point 10 volt and at the B, if you will look, then it is a 40 volt. So here potential is same, everyone. So work done in the third case and in the fourth case also minus 30 joule. So in this all cases, we are getting same work. That's why the correct answer should be what? It should be option B. In all the 4 cases, the work done is the same, everyone. So correct answer is option B. Note down. Let's see next question, everyone. Some equipotential surfaces are shown. Find the magnitude and direction of electric field. So here we want magnitude and direction of electric field. Correct? This green line is representing equipotential surface, everyone. So this is not a line, it is the surface. Correct? So this is 20 volt surface, this is 0 volt, and this is minus 20 volt surface, everyone. We know 2 things. If we will move in the direction of electric field, then potential will decrease. Second thing we know, correct? equipotential surface and electric field always perpendicular. So if we will use these 2 points and we will draw electric field, so electric field direction should be like this, everyone. So this is electric field, everyone. You can see it here. This is equipotential surface. So it is intersecting at 90°, correct? And if we are moving in the direction of electric field, then potential is decreasing also. Here we have 40 volts, then 20 volts, 0 volt. So we are moving in the direction of electric field, then potential is continuously decreasing. And equipotential surface and electric field both are perpendicular, correct? And potential between these 2 points is how much, everyone? If we will find, so what it can be written as, we know that del V equal to minus ED, correct? So what is the del V? Del V is the potential difference. So it is minus 20, minus 0 and 0. So it will be minus 20. So potential difference minus 20, minus E, and D is the separation between these two. So D is what is the perpendicular distance between these two surfaces. So this D we want. So this is 37. So this angle should be what? It is 53°, correct? So here cos 53 can be written as base by hypotenuse, means D by 10, everyone, correct? This distance is how much? It is 10 centimeters. So this distance is also 10 centimeter. So from here we will get D value, and it is 10 cos 53. What is the value of cos 53? See this triangle, everyone. So this is 90°, correct? This is 53. So this is 3, 4 and 5. Angle between 5 and 3 is what? It is a 53°, correct? We want value of cos 53. Cos 53 is what? It is the base by hypotenuse, means it is 3 by 5. So what is the value of D? It is 10 and it is 3 by 5. So how much we are getting? It is 6 meter, everyone. So D value is how much? It is 6 meter. So put here D equal to 6, minus minus will get cancelled out. So we will get E equal to 20 divided by 6. Hence we are getting E equal to how much, everyone? It is 10 by 3 Newton per coulomb. This is the value of E. So magnitude of electric field we got it is 10 by 3, correct? Okay. Now we want electric field in the vector form. Direction already we knows, but now I want to write in the vector form. So let's see it. So E can be written as, if I will resolve this E in the horizontal direction, then component is what, everyone? E cos 53 I cap. And if I will draw or if I will resolve in the vertical direction, then component is E sin theta j cap, and it is present in negative direction, then we will write minus j cap. So it is minus E sin 53 j cap. So what is the value of E? E is how much, everyone? It is 10 by 3 cos 53. The value of cos 53 is how much? It is 3 by 5. E is 10 by 3 and sin 53. Value of sin 53 is 4 by 5. Look at this triangle, everyone. Correct? This is 53. So it is perpendicular by hypotenuse, means 4 by 5. Alright. Now simplify this and let's see what we will get. 3 is cancelling here. This is 5, this is 10. So this is 2. So we are getting here E equal to 2 I cap. And here this is 10, this is 5. So this is 2, everyone. So 8 by 3 minus 8 by 3 j cap. So finally we have electric field in the vector form, and magnitude also we have, it is 10 by 3. So this is the final answer, everyone. Note down.